Let's now look at one way that you can take experimental data and apply a mathematical transformation to it to understand what type of rate law, zeroth, first, or second order, you might be dealing with. This type of approach was particularly popular in the days before computers and computer fitting became widely available, but it's a great way to start to get an intuitive understanding of how one might experimentally measure these. Those more advanced computational methods are something that you'll have an opportunity to learn about in some of your upper level courses. Let's start by looking at a zeroth order reaction. In a zeroth order reaction, you basically already have a linear function. So there's no need to do any other transformation. Starting from your initial concentration, the concentration is going to go linearly down. These types of reactions are pretty rare, and there tend to be some special circumstances involved when a reaction is truly zeroth order. Those will be discussed in some upper level courses. Let's now take a look at first and second order examples. Those are ones that we secretly have already seen the linear versions of. In order to get to this function, we took the exponential of each side to get rid of the natural logs that came out of making the integrated rate law. To make it linear, we just want to put those back in. Here we're going to be taking advantage of the properties of logs yet again to pull out the kt term and make it separate from the initial concentration term. So in this case, you could take your experimental data, take the natural log of each of the concentration values that you observed, and what you should see in that case would be that your data would now be linear. If you attempted to do this approach with a function that was actually zeroth order, you would not get a straight line. You would get data that was curving like a natural log. Let's continue this approach and now apply it to our second order case. In that case, again, we took the inverse to make this into a form that we could properly plot. Let's take the inverse again to bring it back to being linear. And just a sort of quick important side note, I'm being very specific about the plus and minus signs that are showing up in each of these. Again, the reason for those comes from differential calculus, so I'm not going to ask you to demonstrate to me why they are the case. But the important thing to note here is that that would mean that in this case, we would go from our initial 1 over a naught value, and in this case, a second order reaction, we would expect to follow a straight line with a positive slope if we took the inverse of it. So in each of these cases, a straight line can only be put through your data if the reaction actually corresponds to that particular order. That also means that once you fit that straight line, you can gain information about things like the rate constant for the reaction from easily fittable aspects of the line, like the slope. The last thing that I'd like to comment on for this approach to experimentally determining this kind of information is to bring us back to the first order case. Let's imagine some fairly complicated reaction with a rate law that looks pretty serious, like this one. This is a third order rate law overall with a first and second order components in it. Trying to experimentally measure that could be really difficult because the concentration of A and B will both be going down, and they'll be going down in different ways. In that case, a different approach is often taken by experimental scientists who are trying to measure the properties of this reaction. Because each of the reactants can be added independently, it's possible to add enormous amounts of one relative to the other. So we could, for instance, add such an excess of B that as the reaction continues, though B is being consumed, as a percentage, if there's a lot more B than A, each time the reaction progresses, a large percentage of A will go away, but a small amount of B will go away. The impact of that is that we can approximate this term as constant. If B is approximately constant because it's so large that even a whole bunch of it reacting away doesn't make a change, the result is that we're left with a function that is now only dependent, really, on the concentration of A. And now that function will again start to appear very much like a first-order process. As a result, these techniques that worked to measure first-order processes can also be applied to measure other processes if the concentrations can be varied enough to make those other processes pseudo-first-order.